everyone, I'm Professor Harrison, and welcome back to our module on Calculus for Finance. Today we're going to be covering implicit differentiation for comparative statics, which is the technique you reach for when the optimization problem doesn't give you a closed-form solution to plug into. We're following Victor, a hedge fund manager whose edge is slipping and he can't figure out why, corresponding with the rational quant. Today he's working out how the yield on a bond in his book responds to price changes. He opens the latest letter from his anonymous correspondent. There's a class of optimization problems where the direct method we've been using actually breaks. The first order condition mixes function classes that can't be algebraically separated, and you can't isolate the decision variable on one side of the equation no matter what manipulations you try. So you can't write the optimal decision as an explicit function of the parameter, and the direct method has nothing to differentiate. Let me show you an example of what I mean. Imagine a market maker, the dealer side of the trade. The market maker faces order flow from a counterparty whose orders are predictable. Whenever a market parameter shifts, the counterparty rebalances toward an optimal portfolio in a known and expected way. The market maker prepositions to capture that flow profitability. Let X be the market maker's preposition size, and let alpha be the parameter that measures how predictable the counterparty's flow is going to be. After working through the dealer's profit function, the first order condition ends up being 2x plus the natural log of x equals alpha. This is the kind of equation that breaks down through the direct method. The 2x term is polynomial. The log of x term is logarithmic. There is no algebraic operation that isolates x on one side of this equation. So we can't write x star as an explicit function of alpha, and the direct method is not going to be something that we can operate on. But comparative statics still works. The technique is called implicit differentiation, and it relies on a different idea. Even when we can't solve the first order condition for x explicitly, the first order condition itself defines x star as a function of alpha. If we differentiate the first order condition with respect to alpha, treating x as a function of alpha throughout, we end up with an equation that we can solve for dx star d alpha. Let's see this play out on the market maker's problem. Move everything to one side, so the first order condition reads 2x plus the log of x minus alpha equals 0. Call the left side f of x and alpha. Whatever x star is at any given alpha, f equals 0 is satisfied at that point. Now differentiate both sides of f equals 0 with respect to alpha, remembering that x is itself a function of alpha. Using the chain rule, the derivative of 2x with respect to alpha is 2 times dx d alpha. The derivative of log of x with respect to alpha is 1 over x times dx d alpha. The derivative of negative alpha is negative 1, and the derivative of 0 is 0. So we end up with 2 times dx d alpha plus 1 over x times dx d alpha minus 1 equals 0. Now we can factor out the dx d alpha, and we get 2 plus 1 over x times dx d alpha equals 1. When we solve, dx star d alpha equals 1 over 2 plus 1 over x. We can clean that up. Multiply numerator and denominator by x, and the numerator becomes x, the denominator becomes 1 plus 2x. So dx star d alpha equals x over 1 plus 2x. Now plug in numbers. Suppose alpha equals 2. The first order condition says that 2x plus log of x equals 2, and you can verify by inspection that x equals 1 solves it. 2 times 1 is 2, log of 1 is 0, the sum of which is 2. So x star equals 1 when alpha equals 2. The sensitivity at that point is 1 over 1 plus 2 times 1, which is exactly 1/3. So as alpha rises, meaning the counterparty becomes more predictable, the market maker's optimal preposition grows. The formula computes the rate of growth precisely. Pulling back, this calculation is one application of a general formula. Whenever the first order condition is written in the form f of x and alpha equals 0, the comparative statics derivative is dx star d alpha equals negative f sub alpha over f sub x. F sub x is the partial of f with respect to the decision variable, and f sub alpha is the partial with respect to the parameter. In our example, f sub x was 2 plus 1 over x. F sub alpha was negative 1. The formula gives the same answer we just computed by hand. Now let's take a step back from the mechanics and say why this matters. With the direct method, you need a closed-form solution for x star to be differentiable. Without one, you're stuck. And in real-world problems, closed-form solutions are the exception. Most useful optimizations end up with first order conditions that mix polynomials with logs, exponentials with reciprocals, trigonometric pieces with algebraic ones, and you can't just isolate x by itself. Implicit differentiation is what gets you out of that bind. It lets you build a decision rule that says when this parameter shifts by a little bit, my optimal action shifts by this much. And it gives you that rule when even the optimal action itself can't be written down as a clean formula. In other words, you don't need to know exactly what x star is to know how x star is going to respond. That's the part that makes implicit differentiation useful in practice. The class of problems where you can ask sensible comparative statics questions ends up being much larger than the class of problems where you can solve for the optimum explicitly. Victor puts down the letter. Today he's working on a bond in his book. It's a 3-year bond, 5% coupon, with a $1,000 face value currently trading at par. He wants to know how sensitive its yield is to a change in market price. Doing this will allow him to size how much rate risk hedging he needs to do. The question is, if the market price of this bond moves by $1, how much does the yield move? In notation, that's the derivative of the yield with respect to price, or dy dp. Here's why he needs implicit differentiation to solve this. The bond's price as a function of yield is a polynomial in 1 over 1 plus y. Here he has price as a function of yield, and he wants yield as a function of price. There's no algebraic way to invert that polynomial, so he can't write y as a closed-form function of price, and the direct method fails. But the good news is that implicit differentiation will work. The relationship between price and yield is implicit through the pricing equation. Set f of y at p equal to p of y minus 1. Whenever yield and price are consistent with the pricing equation, f equals 0. Apply the formula. dy dp equals negative f sub p over f sub y. F sub p is the partial of f with respect to price, which is just negative 1. F sub y is the partial of f with respect to y, which is p prime of y, the derivative of bond price with respect to yield. The two negatives cancel, so dy dp ends up being 1 over p prime of y. Now Victor differentiates the bond price formula with respect to y. The chain rule applied to each of the three terms gives negative 50 over 1 plus y squared minus 100 over 1 plus y cubed, minus 3,150 over 1 plus y to the fourth. Plug in y equals 5%, sum the three terms, and p prime of y ends up being approximately negative 2,723. So dy dp at 5% yield is approximately 1 over negative 2,723, which is about negative 0.000367. In basis points, that's about a negative 3.7 basis points per dollar of price change. So a $10 increase in the market price of this bond drops its yield by about 37 basis points. This is the exact calculation that duration formalizes. After the calculation lands, Victor sets it down. He understands things now. The market maker example from the letter was about him. The market maker's optimal decision increased with the amount of predictability of the counterparty. By sending these letters, the rational quant made him the predictable counterparty in their example. In doing so, the rational quant went from being a helpful counterparty to being one that's been slowly bleeding him dry, and he has no idea why. Defeated, he writes back to the rational quant one last time, asking what happened. The reply never comes. So that's implicit differentiation for comparative statics. When the first order condition mixes function classes that can't be algebraically separated, you can't solve for x star explicitly. So you set the first order condition as f of x and alpha equals 0. Differentiate it with respect to the parameter while treating x as a function of the parameter, and solve for dx star d alpha. The general formula ends up being negative f sub alpha over f sub x. This is the tool that handles every implicit relationship in finance. Anywhere the variable you care about can't be algebraically isolated, comparative statics will still work because of this method.